Hello. So, this is the last lecture of the course. So, this lecture also is going to be a continuation of the previous lecture, and we are going to solve a example problem and see how Euler-Lagrange equation can be used to obtain the equation of motion of a multi-degree of freedom system. Let us move on to the example. So, the example that we are going to consider today is that of a double pendulum. So, let us take this example of double pendulum where we have two concentrated mass m1 and m2. They are suspended by a string of length L1 and L2 as shown in the figure. Now, this is a 2 degree of freedom problem because the first mass is free to So, the 2 degrees of freedom are theta 1 and theta 2. So, let me write it down. Please note, so this is a 2 degree of freedom system. So, please note that theta 1 and theta 2 are independent of each other. So, the mass m1 can rotate through any free angle theta 1 and the mass m2 can also rotate to another free angle m2 theta 2. So, therefore, theta 1 and theta 2 are the two independent coordinates and they can be taken as the degree of freedom. So, therefore, in the Euler-Lagrange equation u1 is going to be theta 1 and u2 is going to be theta 2. So, as we know, the first job that we need to do is to find out the kinetic energy and the potential energy of the system. So, let us do that. So, let us try to find out the kinetic energy and the potential energy of the system. So, let me just erase this off. So, now let me see what would be the kinetic energy. So, the kinetic energy T for mass m1, it is going to be half m1. We have derived the expression for kinetic energy for a simple pendulum. So, we know that the kinetic energy of mass m1 is going to be half m1 L1 square and theta dot 1 square. This is straightforward. The kinetic energy of mass m2 is not so straightforward. So, the kinetic energy of mass m2 is going to depend on theta 2 as well as theta 1, because it is rotating itself by an angle of theta 2. So, it has a velocity, angular velocity of theta 2 dot, plus it is also rotating some portion because of theta 1. So, the kinetic energy of m2 will also contain theta 1, and how are we going to find out? So, let us first mark this angle. So, this angle is theta 1 minus theta 2. So, what is this? So, this is the kinetic energy because of the velocity of mass m2 in this direction, which is L2 theta 2, that is because of his own rotation, plus L1 theta 1, which is this, and the component of this about this, which is going to be cos of theta 2 minus theta 1, and this L1 theta 1 dot is the component of L1 theta 1 in the normal direction, and that is going to be L1 theta 1 dot sin theta 2 minus theta 1 square. So, if I simplify this, this is the expression that I am going to get for the kinetic energy. Now, let us try to find out the potential energy. Potential energy is very straightforward, and we can easily write that as V is equal to m1 g L1 1 minus cos theta 1 plus m2 g L2 1 minus cos theta 2, that is because of its own rotation, this is because of the own rotation of m1, plus m2 g L1 into 1 minus cos theta 1, right. So, therefore, we get the expression for both kinetic energy and potential energy, and we can solve this. We can use this to write down the equation of motion from the Euler-Lagrange equation. So, now let us get into the Euler-Lagrange equation. So, the Euler-Lagrange equation gives us d dt del t by del u dot j So, for this case, the two equation, this is a 2 degree of freedom. So, j is 1 and 2. So, the two equations that we have is d dt is equal to 0, because there is no non-conservative force. This is equation 1, and the other equation is going to be for the other degree of freedom, which is del t the right hand side is again equal to 0, because there is no non-conservative force. So, therefore, what we have to do is find these two equations. So, let us see what is del t by del theta 1 dot. This is quite straightforward. This is a very straightforward derivative that you have to take. So, del t by del theta 1 is So, this is what we get. Now, let us see what is del L by del theta 1. Del L by del theta 1 is going to be so here t is also a function of theta 1 and theta 2. So, del L by del theta is also going to be del t minus v by del theta 1. So, that is going to be m L1 L2 theta 1 dot theta dot 2 into sine So, this is what we get from the two parts of the equation. So, now if we combine them, we will get the equation as So, this is the first equation of motion. Similarly, we can take the derivative with respect to theta 2 and we can get the second equation of motion. So, now you can see that the equation of motion is very complicated, unlike the simple cases that we were dealing with earlier, and it would have been extremely difficult to get this equation of motion by using the force balance or dynamic equilibrium condition. The other thing you should notice that this equation is a nonlinear equation because it has square of because of these terms. It is no longer a linear equation. So, you can see that even for such complicated cases as that of a double pendulum, the Euler-Lagrange equation becomes very handy in deriving the equation of motion. So, whenever we encounter a very complicated multi-degree of freedom system or even a single degree of freedom system, it is always advisable to use the Euler-Lagrange equation, which involves the kinetic energy and potential energy, to derive the equation of motion instead of using dynamic equilibrium, because dynamic equilibrium uses force balance, which becomes very difficult for complicated cases and it is much more prone to error. Therefore, with this I would like to end this lecture and also end this particular course. I hope you have enjoyed the course and all the best for your exam of the course. Thank you.